Electron configuration helps us make sense of why ions form. And when we look at the electron configuration of ions, we see that many times atoms will gain or lose valence electrons, which are the electrons in the highest energy level, to achieve a stable electron configuration. Many times it's a filled shell. So if we look at cations, cations lose electrons. Here's an example of chemical reaction, if you will, of sodium losing an electron. And if we look at the electron configuration, sodium, we look at the periodic table, has 11 electrons. So here's sodium right here, number 11. And if we were to look at its condensed electron configuration, we would go up to the second period and use neon and then 3s1. So here's the electron configuration of sodium, and when it loses an electron, its electron configuration becomes that of neon. It has 10 electrons. Anions gain electron, and here's a chemical reaction of a chlorine atom gaining an electron. And if we look at chlorine on the periodic table, here it is, number 17, atomic number 17, it's in the third period. To write its condensed electron configuration, we go up to the second period and write neon in brackets 3s2, 3p1, 2, 3, 4, 5. So here's the electron configuration for chlorine. If we add an electron, the p subshell becomes filled, which means we have 18 electrons, which is the electron configuration of argon. Now, when chlorine gains an electron and has the same number of electrons as argon, it doesn't become argon. It just has that same number of electrons. As long as chlorine atom has 17 protons, it's still chlorine. But the stable noble gas configuration is very, very desirable. Likewise, when sodium loses an electron, it doesn't become neon, it just gains 10 electrons just like neon, and thus has a very stable electron configuration. So the main group elements tend to form ions by either gaining electrons if they're nonmetals or losing electrons if they're metals to obtain a noble gas configuration. So remember, the main group elements are in the S block and in the P block. Now, because these main group elements tend to want or are able to obtain the stable noble gas configuration, we are able to form what are known as isoelectronic series, where iso means same. So isoelectronic series is a group of ions and usually an atom that have the same number of electrons. So of course, if they have the same number of electrons, they're going to have identical electron configurations. And the most important electron configurations are those of the filled subshells or those of noble gases. So if I look at this isoelectronic series here, neon has 10 electrons. Let's look at fluorine. Fluorine with an extra electron has 10 electrons. Oxygen with 2 extra electrons has 10 electrons. Sodium, lost an electron, has 10 electrons. And magnesium, who has lost 2 electrons, has the same electron configuration as neon, has 10 electrons. And aluminum, that loses 3 electrons, has 10 electrons. So aluminum plus 3 isn't listed here, but all of these have 10 electrons. Likewise, in this series, potassium plus, chloride minus, calcium 2 plus, argon, all of these have 18 electrons. Now, remember, to figure out how many electrons you have, you take the atomic number, which you find on the periodic table, that's the number of protons, and subtract the charge, and that will give you the number of electrons. Now, if we look at cations of transition metals, and remember, transition metals are right in here, they're filling up the D block. These tend to lose their 4s2 electrons first. So most transition metals have a +2 charge because those 2 electrons in the 4s subshell or the 5s or the 6s subshell tend to be lost first. So go ahead and stop this slide and go ahead and write the electron configuration. Use the condensed electron configuration. for this atom and these two ions. And when you're done, start the video and we'll go over it. So let's start off with platinum. And on our periodic table, here's platinum. It has 78 electrons, and using the condensed electron configuration, I go up to the 5th period and use xenon for the first 54 electrons. Then I go to 6s2. I've got to go down here to the F block, 4f14, and then 5d, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this accounts for all 78 electrons of platinum. Now let's look at iodide. Iodide has a -1 charge, so to count the electrons, we take the number of protons, or the atomic number of iodine, which is 53, and we subtract its charge. So 53 minus -1 is 54. We see that 54 electrons is the electron configuration of xenon. So using the condensed formula, this would be the electron configuration of the iodide ion. Lastly, let's take a look at rhodium plus 2. Here's rhodium here, and since it's a transition metal and it has a charge of +2, those two electrons are going to come from the 5s orbital. So to apply the condensed electron configuration, I go to the period above the period that rhodium is in, which is the 4th period, and krypton, the noble gas in the 4th period, is going to take care of the electron configuration for my first 36. So krypton, since I have +2, I've lost these two electrons, and then it's going to be 4d, 1, 2, 3, 4, 5, 6, 7. So krypton and then 4d7. I have a total of 43 electrons, and those two electrons came from my 5s subshell.